Our next exciting calculus lesson is on Euler's method. So if you remember, you put some calculated programs in your graphing calculator for Euler table, Euler graph, improved Euler table, and improved Euler graph. Now, you can use those if you have many of the steps to do that I'm going to show you today. I'm only going to do ones that use a few steps. But if you had to do this many times, you could use your Euler table or your improved Euler table. So what it's used for is the slope field problems that we solved using separation of variables. If you technically couldn't solve that formula for y equals and find a function for it, you would you still be able to find an approximate value for that differential equation. So it's non-integral, excuse me, means you can't find an integral or antiderivative of it. You can't take the integral of it, and it's a differential equation. So basically it's a slope field graph not solvable to find a separation of variable problem as y equals. So that's all it is. So we're going to use a basic idea of derivative of slope, and we're going to use a basic formula back from algebra, and we're going to basically be looking at finding closer and closer and closer to that point using small steps of the differential equation and increase it by a value that they give us for delta x. We're going to find the delta y, and eventually we're going to find an approximation for that value. Keep in mind the concept is using dy dx, and using the formula we're going to find and solve for it. So back to basics of algebra. We're going to look at slope, delta y over delta x. Cross multiply, you get slope times delta x equals delta y, and that's exactly what we're going to use. Slope in calculus is dy dx. So we're going to take dy dx times delta x to solve for and find the delta y. So here's the idea. We start with an increment of something like 0.1 for, they'll give you what to use for point, or how many steps to use for delta x basically is 0.1. Approximate the value of y when x equals 1.5, given dy dx equals x plus 1. Now I know we can solve some of these dy dx formulas, but the concept and theory behind Euler's method is that you couldn't find an approximate value because you couldn't find the actual function. So they give you where to start, 1, 2. You're going to go from 1 to 1.5 by step of 0.1. So basically you're going to just do dy dx times delta x, and then to figure out the delta y, and then each time you're going to increase your x by 0.1, and you're going to increase your y by whatever delta y is. When you're done, you get your answer for y. So when x equals 1.5 in this problem, it's 3.1. So each time you're basically plugging in the point into dy dx, that's this step, from here to here. Then you're going to be taking the delta x is what they give you. There it is, 0.1. Then you're going to take dy dx, this column, times this column. That equals this one, the delta y. So we're going to add 1.1 to the x, and you're going to add whatever the y was plus the delta y. So 2 plus 0.2 is 2.2, and so on. And you do that for each new point that you're starting with. You always start with the point here, and you apply the process again. Notice that this point becomes the next one, and so on. So here's an example. Approximate y of 1 if dy dx equals negative y. So we can see this is an implicit problem, and we'd have to use separation of variables to solve it if we needed to solve it. Y of 0 is 3. 2 steps of length delta x equals 0.5. And when x equals 0.5, and x equals 1, where are going to be our two steps, because we're going to go from 0 to 1 by delta x of 0.5, which is 2 steps. So we're starting with 0, 3. So dy dx is x over y, whatever the formula is they give you for dy dx. So again, in this case, my dy dx was x over y. So you take the point they initially give you, 0, 3, plug it in, 0 divided by 3 is 0. So here's our formula, delta x equals, you can either use m or dy dx. I like the dy dx. Your formula sheet uses m delta x, doesn't matter. So 0 times delta x is 0.5. So the change in the y is 0. So we add 0.5 to the x, 0 plus 0.5, and we add 0 to the y. So our new point is 0.53. Now we have to get to 1 for the x. So we're starting at 0.53, and we repeat the process again. Negative x over y, not x over y, for the function, dy dx. Alright, so then we do the same thing again. So we take negative x, so negative 0.5, which is a half, divided by 3, or you can go negative a half divided by 3 over 1 is the same as times 1/3, so negative 1 over 6. I kind of like the fraction better, I think I'll use that. And then, to find delta y, we go dy dx, or m, times delta x. So, we take negative 1 over 6 times 0.5, or a half. So again, if I do fractions, I'll keep it in fraction form, is negative 1 over 12. And so my new point, I'm using the old point plus 0.5, 3 plus negative 1 over 12. Let's see, 3 is 36 over 12. So my new point, I add these together, a half plus a half is 1, and where I need to be, 36 minus 1 is 35 twelfths, and that's my answer. So here's another example. We're going to approximate the value of y of 2 for the differential equation x minus y using 4 steps. Delta x is 1/4, given 1, 2 is on the solution curve. So the point we're starting with is, excuse me, 1, 2. We want to get from 1 to 2. Delta x is 1/4, so that would mean we would need 4 steps. Right, here's our information. You should know it's 4 steps because you're going by 1/4 from 1 to 2, which will take you 4 steps. So we're starting with this. We're using the same formula. Delta y is dy dx delta x. I like that one. You can use m delta x again. Alright, so this time here's our differential to plug the point into. We're given the point 1, 2 to start with. So 1 minus 2 is equal to, so x minus y is our function. 1 minus 2 is negative 1. So we take negative 1 times 0.25, or 1/4. So again, I'm going to use fractions. So that would be a negative 1/4. So my new point is going to be 1 plus 1/4 and 2 minus 1/4. So my new point is 5/4, and 2 minus 1/4 would be 8/4 minus 1/4 is 7/4. And, oh, I guess I could have left it there. I'm going to repeat the process again. So, my point was, I'm starting with again was 5/4, my new point, 7/4. My equation for my dy dx again was x minus y. Repeat the process again till we get to our answer. So we do delta y equals dy dx times delta x. We already know the delta x is 1/4, the same thing every time. So I'm going to take 5/4 minus 7/4 to get dy dx, which equals negative 2/4 or negative 1/2. So delta y equals negative 1/2 times 1/4, which is negative 1/8. And my new point, 5/4 plus 1/4, 7/4 minus 1/8. And so that'll be 14/8 minus 1/8 is 13/8. And over here we have 5/4 plus 1/4 is 6/4, or 3/2. So my new point is going to be 3/2, 13/8. I'm going to clear the screen so that I can show the next step. So 6/4, 13/8. Do it again. We have 2 more steps. So dy dx equals x minus y again, same formula. So 6/4 minus 13/8, which is the same as 12/8 minus 13/8, which equals negative 1/8. And delta y equals dy dx times delta x, which is negative 1/32. New point was 6/4 or 3/2 plus 1/4 and 13/8 minus 1/32. So my new point is 7/4 and 51/32. If we do that math, this would be 52/32. Minus 1/32 is 51/32. Okay, one more time. So 7/4, 51/32. And dy dx equals 7/4 minus 51/32, which equals, this would be the same as times 8, so 56 minus 5, 5/32. So dy dx delta y is dy dx times delta x, which is 5/128. My new point is 7/4 plus 1/4 and 51/32 plus 5/128, which equals 2 and 209/128. So my approximation, y of 2 equals 209/128, which is approximately equal to 1.633. If you use your program for Euler and you go step of 0.25, starting at the point that we started at, you should end up with the same answer. So you can always check your work for now on the calculator. If you're going to do the problem though by hand, it'll be a short problem. Probably no calculator though for this kind of a question where you have just a few steps. And that's it for the lesson.